Hi, my name is Jessica, and I'm going to be covering the CRJ 200 hydraulic system. I hope you all learned something from the presentation, and with all that said, let's begin. So the first thing we're going to cover is just kind of some fundamental concepts behind how hydraulic systems work and some of the physics behind that. And then next we're going to go into the CRJ 200 specifics. So we're going to start off. I'll go ahead and play this as a little clip. Thank you to Tech Science for this video. As we can see, when we compare gas and liquid, we find that gas is much more compressible, whereas liquid does not, for all intents and purposes, for our understanding of the hydraulic system, liquids do not compress. So Pascal's law relies on that fundamental principle, that uncompressibility of liquid. Pascal's law states that when pressure is applied to any one individual part of a confined liquid, that pressure is transmitted with undiminished intensity to every other part. So if we take a look at this diagram here, if I apply 100 pounds of pressure on one part of that container, that pressure will be equally distributed throughout the entire container, and all parts of that container will feel 100 psi. The hydraulic system takes advantage of this very principle. So the force applied to a given surface is going to be equal to the pressure multiplied by the area. We already know that the pressure is going to be evenly distributed throughout the entire system. So for example, if I was going to put, let's say on the left side of this diagram, I was to put 100 pounds of pressure right there, and that area 1 was equal to 1 square inch, I would be generating 100 psi throughout that system. On the other side, we see that larger surface area on the right side. We know that I've created 100 psi throughout this system, so now I've got a larger area. Let's say that area was 2 square inches instead of 1. I have 100 psi times 2 square inches, and now I'm generating 200 pounds worth of force on the larger surface. One caveat to this is that you do this work proportionally. So if I put a force on a smaller area, the larger area will move a shorter distance based on the amount of fluid being displaced. So if I, for example, have half the area applying force on one part of the system, the larger surface in the other part of the system will move half as quickly. This is one example of how this might look in an actual system. We would call this a double acting hydraulic actuator because it has hydraulic fluid on both sides of the moving part. The valves in other parts of the system are going to open and close, applying pressure to one side or another depending on the needs of the system. So for example, blue might pressurize and pink will depressurize, and then the device will move to the right. And then vice versa would also happen. Many hydraulic systems will also have what we call accumulators, which allow for the storage of pressure. So what happens is the hydraulic fluid will put increasing pressure on that diaphragm, compressing that air or that nitrogen down. And then in the event of the loss of the primary pressure generating pump or system, the nitrogen will slowly expand, continuing to pressurize the system after the failure. Not only does this act as a temporary backup, but this will also act like an absorber of the pressure energy in the event of a sudden pump-like power surge or like depressurization, allowing for the smoother and more even delivery of pressure, even when maybe that system is not acting as smoothly as it could. Because of these properties of liquid, we can have one or multiple pumps working in one part of the aircraft that deliver work anywhere we want to on that same aircraft. In the CRJ 200, we have 3 different hydraulic systems that don't share liquid. So if one starts leaking, the other 2 will not be impacted. We see these represented by the different colors there at the diagram on the right. We see green, pink, and orange. These systems are not named particularly creatively. They're literally just called systems 1, 2, and 3. here is the screen. So this is what's going to look like to the pilots that displays what the status of the hydraulic systems are at any given moment. All three systems have 2 pumps. That's for redundancy. Each system also has its own dedicated nitrogen accumulator, just like what we talked about on the previous slide. And each system can normally produce 3,000 psi. All of them use this same type of hydraulic fluid called Skydrol. Side note, if you've ever heard of Skydrol, you probably have also heard of how corrosive it is. It's the type of liquid that literally will burn holes right through you. It doesn't matter if it's skin, clothing, this is very dangerous. So if you ever find or suspect a leak, it's important that you don't touch it and you inform the people around you so they're not also risking burns. So we're going to go ahead and start by talking about System 1 and System 2. System 1 here is described in green, and System 2 is orange. Those two systems are almost perfectly identical. They do have some minor differences. They both have one primary engine-driven hydraulic pump and then one backup AC electrical pump. The naming scheme for these pumps is fairly intuitive. You've got 1A and 2A. And that's going to be the engine-driven pumps for both System 1 and System 2. And then we've got 1B and 2B, and that's going to be the backup electrical pumps. The 2 backup electrical pumps actually get their power from the opposite side AC bus. So the right-hand 2B gets power from the left side AC bus and vice versa. This is for redundancy, so if for whatever reason there was an engine failure, both 1 and 2 hydraulic systems will still operate. One of them using AC power from the other engine, and the other using the engine-driven fuel pump from that same engine. Here we have a brief list of each of the different systems on hydraulic systems 1 and 2, and we'll be covering those at later slides. Hydraulic system 3 is slightly different than the other two. It's outlined here in pink. It only has 2 electrical pumps. It does not have an engine-driven pump. These pumps are called, you can see there, 3A and 3B, and they get their power from the AC buses. This here is a short list of what System 3 powers. Before we move on, let's talk about how you would access this system page in the plane. You would actually want to hit the hydraulic button on the ICAS control panel, and it's shown there. The flight controls are controlled by the different hydraulic systems, and each of the hydraulic systems has different distributions on what controls they take part in. Systems 1 and 2, as you can see, are fairly similar in their reach. One minor difference is how the System 1 hydraulic powers the outboard spoilers, and number 2 powers the inboard. They act symmetrically, each controlling their respective ailerons and spoilerons. And then System 3 acts as a further redundancy on the primary flight controls. While the landing gear are hydraulically powered, they are electrically controlled in normal operation. System 3 usually does the work for the extension and the retraction of the gear entirely by itself. However, in the event of a System 3 failure, the gear can still be extended by the manual release handle. This handle relieves the pressure in both sides of that actuator, so the retraction and the extension, allowing the gear to fall down naturally with gravity. It then connects hydraulic system 2 to the downlock assist actuator to ensure the gear is locked in place despite not being extended normally. So the brakes receive pressure from both hydraulic systems 2 and 3. Interestingly enough, System 3 actually powers the inboard brakes, while System 2 powers the outboard brakes. This is good because in the event of the failure of one of these systems, we still have symmetrical braking. However, you do need to keep in mind that your braking action may be reduced by 50%. If they both fail, there should be around 6 braking actions worth of pressure left over in the system from the accumulators. So you should still be able to stop the plane even if they both failed. The parking brake, when you're done with the day and you're all wrapped up, the parking brake runs entirely off of System 3 and will bleed down about 25 minutes after shutdown. So keep in mind the aircraft needs to be chocked or otherwise locked in place before then. One last system to review here before we wrap up. Like the gear, the nose wheel steering is electronically controlled but hydraulically actuated. The pressure for this is only provided by hydraulic system 3, and the steering control is only on the captain's side. I hope you enjoyed that lesson, and I want to say thank you to the above sites for their wonderful diagrams. Hope you guys have a good evening. I'll see you.